the structure and they found that Watson and Crick had something else and this was all wrong. In fact, Watson and Crick also had come up with the same structure with the two standing inside. But I think they had, what's her name? She was the one who had the crystal structure to it actually. I mean, the first crystal structure these people looked at and came up with all their things. And apparently she was absolutely brilliant. She took one look at the structure and said, this is all garbage, it's wrong. Don't even try pursuing this. Probably there was nobody to tell Pauling that, and therefore he went ahead and published it. And somebody apparently said, if only Linus Pauling had read the book, The Nature of the Chemical Bond properly, he wouldn't have made the mistake. And for those of you who don't know, the chemical bond is written by Pauling himself. So they said, if only he had read that book properly, he would have made that mistake. And another person who said, if this had been a freshman chemistry term paper, I would have given him an F in the course. If you can't even recognize that two chart species can't come close to each other. But the point is, that was an interpretation. And Pauling's reputation didn't take a beating for it, you know. Maybe people had fun behind his back because it's always nice to see somebody as intelligent or as big as Pauling make stupid mistakes. It makes you feel nice, you know, because now when I make those mistakes, I can say, well, that's not very, very different. The point is the experiments must be right, and therefore, that's the point I'm trying to make. So you always cross-check, you come back, you do it with two different numbers, with two different states, get the same value, take the average, and then get the average. Now, if you want to be statistically very correct, you take the average, you do standard deviation, the mean, and all that, and then your paper looks good. Okay. Therefore, I have B1, and the B1 is, let's say, 10.1. But let me go back and look at, let's say, I want to know B0. What would I do to get B0? I need B0 also. To get B0, just the opposite. I have to keep a common upper level and keep two different lower levels. And that is going to be the following. For example, if I go from 0, where would I end up at? And if I go from 1, where else can I end up at? So I keep 1 as my common upper level. I go from 0 to 1, and what state is that? What line is that? The R0 line. And I go from 2 to 1, and that's going to be the P2 line. And the difference between the R0 line and the P2 line must be equal to 6B0. And then you do that, R0, I'm missing, I think it's 29.45.8, which is R0. And the P2 is 28.43.3. And P2 is which line? This line. And that's 28.43.3. And the subtraction here is going to give me 62.5, and that's equal to 6B0, and then for B0, 10.42 wave numbers. Of course, what you then do is keep a common upper level J2. I had a common upper level as J1. Keep a common upper level as J2, and look at the two transitions coming from the lower state. You get another value for B0. And compare these two B values. I think you have done it for you. In one case you get 10.42, in the other case you will get 10.46. You know you're okay, take the average, and the average will be 10.42. So you eventually get B0 as 10.42 wave numbers, and you get B1 as 9.79 as the average. Because I got 10.1 in one case. If you take another set of levels, you get something else. Take the average, it will be something like 9.8. Therefore, you get these two. And then what did I ask you to do in that case? I said, calculate R0 and R1. Because if I had given this in the exam, it would be quite a problem because we have to calculate B0, B1, and then I said, can you predict the value of B2 for the B2 level and so on. It's a pretty large problem. So you will get parts of this. I won't give you this as one problem because it will take you about half an hour to complete or so on. You because B naught will then be h by 8 pi square I. And then there is grounds, there are enough opportunities to make errors over there. So be careful. But if I ask you to calculate B0, R0 and R1, you know how to do that, because this is h by 8 pi square IC, this is again h by 8 pi square IC. You calculate R for these two states and you get your R0 and R1 for the two states. We know as we go up what happens to R. It increases. If R increases, what happens to B? It decreases. And that's it. Very rarely you will find that as you go up, the R goes the other way. I think that's probably one case that comes to mind, the lithium hydride. The potential is very weird. But otherwise, most cases, higher B's will have lower values than lower B's because higher B's sample greater R values, and therefore do what's this. So when you ask me this question about flow electronics, this is basically what it is, and this is basically what I'm trying to figure out. So if I say this is R0, I'm basically looking at vibration plus the rotation transition. Vibration plus the rotation transition. Therefore, I'm jumping into another vibration state and the rotation state at the same time. How do you get the B2 value for the molecule from this? There is a little equation which says that B for any state B equals BE minus alpha into B plus alpha. And where alpha is actually a constant that sort of couples the rotation and the vibration problem. This is the rotational problem, and this is the vibrational part. And alpha therefore essentially couples the two for you. So if I know BB and B, in this case I know that. I know for B equal to 0, B is 10.42, and for B equals 1, B is 9.79. You basically write out two simultaneous equations. It's going to be 10.42 equals BE minus alpha into 0.5, and 9.79 equals BE minus alpha into 1.5. And once you have these two equations, you basically solve for BE and alpha. I'll give you the values, just cross-check them out for yourselves. Alpha is 0.33 and BE is 10.61. B has to be even larger because as it gets lower and lower, the R value actually must get smaller and smaller, and B must get larger and larger. So B is 10.61, and what is B really? It is the rotational constant corresponding to the minimum of the potential well. So from which if you now calculate BE and hence you calculate R, that R is actually going to be the value of R for the minimum of the potential well, which means that that's your RE and that BE actually corresponds to that position in your potential curve. So what would always give this data and say give me the average initial distance corresponding to the minimum of the potential well. All you have to do is to get B0 and B1 for two different states, then calculate your B from that equation. Of course, in real life, that's not the way you would do it. Why? Because you've got so many lines out there, and what are you doing with it? So you will actually use a whole bunch of lines and get B0, B1, B2, B3, B4, as many as you possibly can from that data, and then do a fitting of the B value versus B plus a half, and the B and B will be your intercept and alpha will be your slope, and you therefore get your B values and alpha values actually out of a linear least squares fitting routine. And once you have that, that's supposed to be good because you really have a value that is produced out of data that spans a good region of your vibration space. But I don't expect you to do that. Just get me two values B0 and B1 and get me the BE and the alpha value out of that. And once you know alphas and the B's, all you have to do is to see what will happen when I put B equals 2. Then this 10.61 minus 0.33 into 2.5 will be the value for B at B equals 2. And therefore you will get that situation sorted out. So you can take this and have the many different problems of your own that you can build up. You can be asked BE, you can be asked B2, B4, whatever, and this is the way it will go. And you can rest assured that something like this will be given in an exam, some spectrum of either this molecule or carbon monoxide or BCl or what have you. And you will be asked to actually figure out some of these parameters starting from the spectrum. Of course, in my exam, you are still allowed to bring that one sheet of paper written on one side only. If it's on both sides, the paper is confiscated. You can't use it, it must be only on one side. And within that one side, summarize whatever it is that you need to summarize for the course. And A4, not something Any questions on this? Before I just go to the fifth problem. The Banwell problems, I will come back. I'll probably have the other session on Friday too, if you wish. We'll go through the problem sets. I was hoping to teach you something more on electronic spectroscopy vacuum, and I took that, but that's okay. I can always do it later. I will finish this, and then we look at the problems in Banwell. And if there's time on Monday, then I will go back and do a little bit of atomic spectroscopy and electronic spectroscopy vacuums, and then into that also into an exam. But I probably won't teach you a whole lot on Monday because I don't wish to dump things for you the last minute and expect you to understand what's going on. But I will try to complete the picture that I started off to paint a little by little on 2 classes ago. Let's take the fifth problem. And again, here you have to be obviously careful in the way you handle numbers. It's trivial, but there is enough scope for mistakes. The neodymium yak laser, and that's the way it's written. The yak actually stands for yttrium aluminum garnet. It's actually yttrium oxide and aluminum oxide, in which you have a neodymium 3+ ion that's actually doped inside. It's a nice ceramic rod, and into this rod, if you actually shine light, you will find that there is a lasing action that will set in. After I've done electronic spectroscopy of molecules, maybe half a class or so, I will talk to you about lasers and how it's produced and how, I don't know whether you've already done it in physics, and how it is used in spectroscopy. Spectroscopists use it all the time for various measurements. As I said, Raman Spectroscopy essentially became extremely popular only because the lasers were on. And the lasers are not just another more intense light source. There's nothing. It's not just an intense light source. It's got some very nice properties. It's got coherence, it's got monochromaticity and all that, which makes it an extremely useful. It's a source of a different class altogether. If you just wanted more powerful sources, all you had to do was go to the cricket ground and get these huge floodlights that they use. That's enough. So they're all intense lights. The laser is still very different. It's intense, but it's extremely different. Okay, now let's do this. The wavelength of this laser is 1064 nanometers. And all I'm saying is that it's used to record the rotational Raman spectrum of nitrogen. Calculate the wavelength. You will do one of them. Is scattered radiation. Calculate the wavelength of the scattered radiation. So I really want you to find out when you do the experiment, what's the wavelength of light you're actually going to measure, and that's what I'm asking you to do. So find out the wavelength of the scattered radiation for the rotational Raman lines indicated below. I think the first 2 lines is 0. And what does that mean? It's a rotational Raman spectrum. We don't go writing all the vibrational. We only like to note V equal to 0, that's 2B, 6B, 12B. And the 0, 1, 2, 3. And if it's an S0 line, what's the transition gradient from? 0 to 2. And somewhere down below, I have said the rotational constant B0 for nitrogen is 2 wave numbers. So if B0 is 2 wave numbers, what is this going to be? Is this going to be 12 wave numbers? That's difference. And all I'm asking you is to figure out what the frequency of the scattered yarn radiation is going to be. So I'm shining 1064 nanometers onto my sample, which is nitrogen gas. and I'm looking at the scattered radiation at 90 degrees, and I'm going to get a bunch of them, and I'm asking you to figure out what the frequency is for the S0 line. And S0 is 12 wave numbers apart, so all you need to do is take this, convert that to wave numbers first. So if lambda is mu bar is going to be 1 over lambda, and that is going to be by wave numbers. So you must show it to me. Don't have this calculation done the last page somewhere and time to find an answer. Again, going to hurt you. Show this in this way. And then it's a Stokes line. If it's a Stokes line, what do I do? Do I subtract or do I add? That's basically what I need to figure out. The frequency is going to be longer. The energy is going to be smaller. And therefore, the frequency of the Stokes line bar is going to be 93, 98.5 wave numbers minus S12 wave numbers that's gone for the transition. So the molecule actually goes from here all the way up and comes back and lands up here. And the frequency of the scalar radiation is going to be that minus this, which is what I have over here. And that's going to give me something like 93, 86.5 wave numbers. But then I also said give it to me in nanometers. You're going to make sure you convert this back, and when you do that, it's 1065.36 nanometers. So I'm shining light at 1064 nanometers, and what do I get out of it? 1065. So essentially it means it's a 1 nanometer shift or 10 angstrom shift. Now most spectrometers will have the resolution to easily see 10 angstroms. The resolution typically is the order of 0.5, 0.1 angstroms. It's very easy to get. But the problem over here is going to be, this is going to be quite close to 1064. And what is 1064? It's input radiation. And what is that going to be the same as the Rayleigh scattering? And Rayleigh scattering is going to be intensely. Therefore, you have to put a filter out there to cut off the Rayleigh scattering. So if you have to cut off the Rayleigh scattering, this filter will have a certain bandwidth, or it will have a certain region through which it will allow or prevent light. If it prevents light from going through it for, let us say, plus minus 20 angstroms, or then you are finished, you will not see this line, because the filter would have stopped it. So generally what you try to do is to have a filter that is quite narrow band, which is sort of cut off maybe a few angstroms on either side, and then let the rest of the window be open for you to be able to see the scattered radiation coming off. And that's the way this would happen. So this is for your S0. I also asked you to do it for S1 and the first anti-Stokes line for S0. With the anti-Stokes line for S0, it is going to be plus out here, and you will find that this would not be what you have, it is going to be something else. It is 1062.6. This is the anti-Stokes lines. So your anti-Stokes lines will come at shorter wavelengths, the Stokes lines comes larger, and therefore you have to work it out that way. So I think what is left behind is all those problems that have been worked out in Banwell, work them out, and you will sit down again on Friday and take a look at these problems before I go on to do something else. Please remember what I said in the class to begin with. I know this does not apply to majority of the class. I apologize to the rest of you that I may be saying this. But I hope the message, please listen here. I hope the message goes to the people who are doing this. And if this is not stopped, you will have serious problems. So please stop this and only sign for yourself. There is no need to outsource signatures. You do it the way, you just do it for yourself. You don't have to outsource it. But if it's done, it's going to be serious.